Okay, some more problems from section 9.4. This is number 27. And we run into a little issue here, and I'll talk about that in just a second. So if we take a look at this geometric series, it's obviously a geometric series because you've got your nth power here. So this is my ratio. So r equals x squared minus 1 over 3. We want to find the interval of convergence. So we know that it converges for the absolute value of r less than 1, so we set that less than 1. And then if we followed our normal procedure, we would have some problems, because what we could do is we could say that we could just take the 3 out or underneath it and say it's just the absolute value of x squared minus 1 over 3 and multiply both sides by 3. And we could get something like this. I'll just show you what I had done before. And then if we break this up, we put this in the middle, we'll say that x squared minus 1 is between negative 3 and positive 3. And then if I add 1 to both sides, this is negative 2 and 4. And then if I want to find out what x is, I've got troubles, because I can't take the square root of everything, because I can't take the square root of negative 2. So I have some problems if I deal with it like this. So this is a way you can handle a problem like this. Okay, again, it's going to be true that when the absolute value of this is less than 1, that's going to be true. Now, that's going to be the value of a function will be less than 1 whenever the numerator is smaller than the denominator. So what you can do with this is you can say, well, this is going to be less than 1, all right, when the numerator is less than the denominator. X squared minus 1 is less than 3. Okay. Now you might say, well, how are we going to get our interval convergence from this? Now, kind of bear with me, and I guess you'd use this approach, when you have a square term like this. Okay. So what you can do is then you can add 1 to both sides, and you get x squared is less than 4. And then you can take the square root of both sides, and you get the square root of x squared is less than the square root of 4. But please remember that the square root of x squared, that's another way of writing the absolute value of x. Just kind of remember this, because this shows up more than one time, or more than one area. We see this lots of times where we see the square root of x squared, and instead of writing it like that, it's a piecewise function, we could write it like this. It behaves the same way. So we can say the absolute value of x is less than 2, and then I can break this up and say that x is between negative 2 and 2, and that's going to give me my interval convergence, which will be negative 2, comma 2. And that will be my interval of convergence. Okay? So that's kind of a somewhat bizarre problem, but that's the way you have to deal with it, because if you tried it the other way, you would end up with a dead end. Okay, now the sum. Again, this is my r, so we can do our sum using the sum is a, which is the first term. In this case, is 1 over 1 minus r. And then we just multiply the top and the bottom by 3. And then we can simplify. So 4 minus x squared, so there's your sum. So that was easy. That was the easy part. Okay, 28. This is another one that we have to use some little arithmetic hijinks here. The summation of n equals, from n equals 0 to infinity, the sine of x over 2 to the nth. So there's my r is the sine of x over 2. So how am I going to get an inequality involving that? Because I know the sine of x is always between positive 1 and negative 1. What I could do is I could say that I want, well, I know that since the absolute value of the sine of x is always less than 1, right? Because sine of x oscillates between negative 1 and positive 1. Since I know this, for all x, I can say that the sine of x over 2, the absolute value of that, is less than 1 over 2, because that's just 2, and we know that the absolute value of this is less than 1. So I can write it's less than 1 over 2, which is less than 1. Well, that's going to be the case for all x, all right, because the sine of x is always, if this is my r, and since the largest this can be is 1, this is always going to be less than 1 over 2. Or the absolute value of it for sure. Will always be less than 1 over 2. Less than or equal to 1 over 2. So that's less than 1, so that means it's going to for all x, that means it's going to converge for all x, so from negative infinity to infinity. So that's the radius of convergence. Okay, or I should say not the radius of convergence, the interval of convergence. Pardon me. Okay. So again, we just have to know that we know this, the absolute value of the sine of x is always less than 1, so that implies that this is going to be less than 1/2. And since 1/2 is always less than 1, then it converges for all values of x, so the interval of convergence is a negative infinity to infinity. Okay? All right, then number 2930, we just want to determine the convergence or divergence of the series, identify the test or test you use. There may be more than one correct way to determine the convergence or divergence of a given series. This is my first one. And we've dealt with this limit so much we shouldn't realize that the limit as n approaches, as n goes from 1 to infinity, of this, the limit of this as n approaches infinity, of a sub n each term, or the nth term, is not going to be 0. Remember, the limit as the nth term approaches infinity must be 0 for it to converge. Well, since it's not equal to 0, actually the limit is equal to 1, that's not equal to 0, then it diverges by the nth term test. In other words, if you look at the nth term as n approaches infinity, all right, if that value of that term does not approach 0, then it can't converge, therefore it must diverge. Okay? And the last one on this little section, number 30, take a look at this. And we have the same situation. If I look at this limit as n approaches infinity of the nth term, that represents the nth term, so as n goes to infinity, what's going to happen? Well, this is going to get really, really big, much bigger than this does, so it diverges by the nth term test. Now, if that's a little bit hard for you to kind of see that limit as n approaches infinity, because the top actually goes faster than the bottom because we have an exponent, and then we just have a linear power. We can use the ratio test. Let's try the ratio test. So I'll take the limit, and I'll have 2 to the n plus 1 over n plus 1 plus 1, and then times the reciprocal n plus 1 over 2 to the n. And then what I can do is I can take this 2 to the n and write it as 2 times 2 to the n, because it's like 2 to the first. And this is n plus 1 plus 1 is n plus 2. And this is going to be my n plus 1 over 2 to the n. That's my reciprocal of the denominator. And these 2's cancel, so it leaves me with 2 times n plus 1. Now in this case I multiply it out, 2n plus 2. And then this was just 1, and so over n plus 2. And then look at these, look at the highest degree terms. They're both n to the first power. So what's my limit as n approaches infinity? The ratio of the coefficients, which is 2 over 1, which is 2. So since that ratio is 2, okay, or since that limit is 2, pardon me, since the limit is 2, since the limit is 2, then that's my L. L is greater than 1, so therefore the series diverges. So you can also prove it by using the ratio test. Okay? All right, so I hope this helped.